Swayam Prabha, Digital India, Educated India.
So last class we discussed the derivation of current through the diode. So what we did, we solved a minority carrier diffusion equation, right? And when we solve the minority carrier diffusion equation, we obtained the expression for diffusion current. Okay, so we were discussing the diode current. So when we solve the minority carrier diffusion equation, we obtain the diffusion current through the two regions. So let's say you have P region here, N region here, right? And we added these two current at the two ends of the depletion region, and we said this is the total current, the addition of two current, right? Then from this expression, we can also get an idea of a, let's say, if you have some P plus N junction or N plus P junction, one-sided junction, right? So in that case, the number of carriers which are injected from P side, they will be much larger, and this current will be much larger, right? So these injected holes will dominate. So only one of the term will dominate here, right? Now if you see here P plus, that means minority concentration is very less here, right? So this will be very less, right? For P plus, the minority concentration is NP0, right? So this first term will dominate for P plus N. For N plus P, of course, the second term will dominate. So this is basically one-sided junction. And for one-sided junction, you can see that current, if you want to increase the current, what you have to do? You have to increase this P or holes on N side. You have to increase the holes on. And how can you do that? You can decrease the doping, right? So for P plus N junction, if you decrease the doping on N side, that is ND, donor concentration, the diode current will increase. So this is the overall expression. And this is basically the current density, right? So if you want to get the current, you have to multiply this by cross section area. Okay. Now there is another simpler way to drive this current equation, that is called charge control methodology, right? Because in the steady state, the charge that is injected here, right, is constant because you are not changing the voltage, right? So for a given voltage, this injected charge, the profile is same, right? So now if you see how much charge is injected, right? So that is basically delta N as a function of X and delta P here as a function of X. Now this has a lifetime tau, right? It has a this charge, it has a lifetime tau, right? So the current will be the charge, total charge that is here, Q divided by tau, right? So this is basically injected carries are P here, so this becomes tau P. This is, let's say, Q1, this is Q2, injected carries are electron, so this becomes tau N, and you add 2, basically you get total current, right? So that you can see here. So for example, this is the injected electron concentration to the P side, and this is the boundary of depletion region from minus XP to XN, and this electron concentration here will decrease as you move away, right? So there are two things here. This carrier is diffusing as well as this carrier is recombining. So we know about diffusion length. Diffusion length is square root of d tau. So the concentration will look something like delta N, you can say P naught, the maximum here, e to the power minus x by L, right? Now this is in negative x direction, right? So it has to be plus x. Now here origin is shifted by xp minus xp. So you can write here instead of x, you can write x plus xp, right? So that's what you get here. and delta n is of course np naught exponential qv by kt, because injected carrier density we already calculated in previous class, that injected carrier is basically magnetic carrier concentration times exponential qv by kt. So delta n become np minus np naught, right? So you get this expression. So when you integrate this one, you get total charge, right? So total charge is basically integral of this thing from minus xp to minus infinity, right? And that you basically get the same expression. And when you divide this by, now this is a total charge. The total charge divided by tau. The tau is what? L by tau. You can see here. This L square is d tau. So L by tau you can write tau by L by tau becomes d by L, right? So L by tau you can write d by L, right? So basically you get the same expression, right? You see here d by L, right? Qp d by L, right? So this is Qn d by L, right? And you can basically add these two currents due to the injected electrons and other due to injected holes. That expression will also be similar. So overall current will be the sum of these two. So you can add these two and you basically get the total current. Okay. This I will discuss, right? Because L by tau is written as d by L here. And similarly, expression for holes, you have dp times p naught by lp exponential qb by kt minus 1, right? So if you add these two, you will get total current. Now expression is same whether you use the magnetic carrier diffusion equation or this charge control method. However, there will be the procedure will slightly change if the length of the region is not large. Now when we say infinite, right? Of course, in real life you will not have a infinite n region or p region, right? So when we say infinite, that means this length here is much larger than the diffusion length LP or LN, right? This is okay. It is much larger than the diffusion length. So that is basically we are considering it infinity, because here it will reduce down to a very small value. So delta n will go to 0 here, or basically n will be equal to np naught. Now sometimes this length may be small, so basically a contact may be here, right? So this length is comparable to diffusion length, right? In that case, what will happen? This will slightly change, right? Now at the contact you cannot have this much concentration, right? It has to go down, right? Because extra carrier will recombine at the metal junction. So this process will slightly change. You can try it now, and we will discuss in coming slides. So this is basically the expression for total current which you obtained from charge control methodology. Now let us analyze this thing more further. In forward bias and reverse bias, what does this current equation tell us? In forward bias, this V is positive, right? In reverse bias, this V is negative, right? So here, what will be this delta NP? For forward bias, of course, it will go up. In reverse bias, this will go down, right? Now it cannot go arbitrarily go down. Maximum, the minimum concentration possible is 0, right? Delta n can be minimum can be minus np naught, right? It cannot go below that, right? You cannot have negative concentration. So in reverse bias, this concentration will go down. In forward bias, this injected concentration will go. So this is called injection, and this is called carrier extraction. So in forward bias, we inject carriers, or carriers are injected from other side across the junction. In reverse bias, these carriers are extracted. Now these are magnetic carriers. So you can see the picture here, both are shown. This is forward bias. So in forward bias, from P side, holes are injected. From N side, electrons are injected, and this is their concentration profile. And due to this, there is a diffusion current. And the direction of diffusion current is basically in the direction of hole, right? So overall current flows in this direction from P to N. So if you connect a positive here, negative here, current is flowing from positive to negative. And how do you compare different currents? In depletion region, of course, we assumed that there is no generation recombination. So the current is constant throughout the depletion region. So the carrier that are going through the depletion region, they are passing by it basically. So nothing is happening with them. So the current is constant. At this interface, at x equal to xn, so the junction between the depletion region and N region, this is basically the diffusion current, which is quite high. And the expression for diffusion current is same as the expression for magnetic carrier concentration, because it's exponential function. So the derivative is also exponential. So the current is basically directly proportional to the delta N or delta P, and it is reducing. Now overall current has to be constant. So if this current is Jp, this will be J total minus Jp will be Jn. Now this current is drift current. Now as we discussed earlier also, drift current requires a field, but we assume this to be quasi-neutral region, right? So that means field is very small. Now why? Because to carry the same current, if there are large number of carriers, it will require very small field. So that field is very small. We can say it's almost neutral, no field or very negligible field is required. So as you progress away from the junction, the diffusion current goes down and drift current takes over. Now this drift current is due to majority carriers. This is due to majority carriers. And this diffusion current is due to minority carriers. Similarly, on other side, P side, this is a diffusion current, Jn, and this is J minus Jn, which is Jp. Now if you see here, you can see these pictures and tell which side is highly doped, N side or P side. You can compare, of course, this magnetic carrier concentration, because both are silicon, NP product is same. So if magnetic concentration is more here, that means the doping is less here. So N doping is less than P doping. Or you can see the number of carriers that are injected. Now for the same potential, number of carriers that are injected is more here. So that means P doping is more. That means the current contribution due to holes, minority holes will be more than the minority electrons. And if this gap is large, then you can say, okay, so this is the forward bias discussion. Now in reverse bias, what happens? Instead of injecting, the carriers are extracted. So here we injected minority carriers. Here we are extracting the minority carriers, right? Because it's a reverse bias. So these holes are extracted from N side, electrons are extracted from P side. So the minority carrier profile looks like this. And of course it can go to 0 only, it cannot be less than that. So even for a few kT, this will go down to almost 0. Now if you see here, the slope is in opposite direction now, right? So when there was forward bias, slope was like this and these carriers are moving away. In this case, slope is opposite, so these carriers are basically moving towards the depletion region, right? So that means the direction of current flow will be from N to P. And what was the current? Now again, this is the diffusion current, right? Due to the N, this is the diffusion current. This is the diffusion current. And here also, if you see here, the slope is large here, slope is getting smaller. So the diffusion current is larger again at the interface, right? So here basically the concentration is increasing, but if you think of delta N, right? the magnitude of delta N is decreasing as you move away from the interface of the depletion region and the N or P junction, N or P quasi-neutral region. So the diffusion part is basically decreasing as you move away. So basically you have a similar thing, but the direction of current is reversed. And of course the magnitude will be small, right? Because now delta N or delta P is simply NP naught or PN naught, right? And here it is NP naught or PN naught multiplied by exponential factor. So in reverse bias, how much current you can have? Let's analyze this expression. In forward bias, your carrier concentration can move up to e to the power qv by kt, so it will appear there. In reverse bias, this is e to the power minus qv by kt, so you can say this is basically very small. You just have -1 here, so only this current will flow, the coefficient, and this is called J naught or reverse saturation current. Or you can see here the current ratio will basically be Pn naught by LP, right? So you can see here Pn naught by LP, right? So only this coefficient here, which is called reverse saturation current, that only flow, right? Now I give you one homework here. What you do? Let's say this, the length of the N region or P region is short. This length is comparable to Ln or LP, right? In that case, what will be the current? So all of you try this one, and we can discuss in the tutorial. So this is for finite width, for finite quasi-neutral region. Please calculate the expression for current, how this expression will be modified. So here what term we will have, because now length is shorter than diffusion length, so how this will be modified. So is it clear? Okay, now this is the IV curve for ideal diode characteristic. So basically in forward bias, current is increasing exponentially, and in reverse bias is more or less constant. Now this is the equation for ideal diode, right? Where we made certain assumptions. And this you can also plot on log scale. So in log scale, because it is exponential, so it will just be QVA by KT, right? So exponential will be Q, the slope will be Q by KT, and this will intersect y-axis at log of I naught or reverse saturation current. So this is for ideal diode, right? Now in real diode, there will be recombination also in the depletion region. There will be generation also. There will be some series resistance. So let us look at a diode. So in this depletion region, there will be generation, there will be recombination. This region will have certain resistance also, or called series resistance. So how these factors will change? So they will affect the diode IV characteristic. So this is a typical IV characteristic of real diode. This is taken from your textbook. So do you notice any differences with the ideal diode? One difference is very obvious here. When you go to reverse bias, a certain voltage you see, a sudden increase in current. Another thing is not obvious in this picture, but when you plot on log scale, right, the slope is basically different, right? Here slope is Q by KT, here is Q by 2 KT. So basically slope is usually written as Q by eta KT, right? Where eta is the ideality factor. And another thing you notice here, for reverse bias, if you see here, this current is increasing. So this current is not constant. As we derived for ideal diode, we said this reverse saturation current is constant, but this reverse saturation current is actually increasing, right? And if you notice it carefully, it appears to increase. It does not increase linearly with the voltage. It increases as a square root of reverse bias voltage. And of course, this is basically the a sudden increase in current, right? This we call breakdown. So a detailed discussion. So for forward bias up to 0.3 volt, right? So between 0 and 0.3. So these values are not very hard, but close to that. The slope is Q by 2 kT. Now, in your ideal diode, what is the slope? KT by Q, right? So from 0.35 to around 0.7, the slope is very similar to ideal diode. And of course, when you increase the voltage beyond 0.7, the slope again goes down. Slope actually reduces. And if you see the intersection here, this line intersects around 10⁻⁻14, so that becomes your reverse saturation current. Now what you can do, if you want to see this picture, you can refer to some data sheet. Take a data sheet of a diode, and you can see all those characteristics of the real diode. Now in reverse bias, it is order of magnitude different. You see here, the magnitude is few hundred picoampere, and start with microampere. So there's a difference of 10⁻³ magnitude. So reverse bias current is 10⁻³ times smaller. It should not be larger, it should be smaller than forward bias. And it does not saturate, of course, it increases with the voltage. And there is a breakdown. There are two breakdown mechanisms, avalanche and Zener. Avalanche is basically due to high energy electrons and holes. These bonds are broken and electron hole pair is released. Zener is basically tunneling. Now tunneling will happen when the barrier is narrow. Now in which case the barrier will be narrow? Barrier is actually your this depletion region, you can say, right? Now in which case the depletion region will be narrow? When doping is high, right? So Zener tunneling is usually seen for high doping. Now let us discuss them one by one. Now in case of avalanche breakdown, what happens? There is very high field, right? So let's say electron come from here, and as it moves a certain distance x, now field is E. So energy it has acquired will be, voltage is integral E dx times Q will be the energy, QV. So if this energy is large enough to break down, then it will generate electron hole pair. Now these two will generate 4 will generate 8, right? So like this it will happen. So when the multiplication factor is more than 1, right, they will basically keep on increasing. Now this electron hole pair, this hole will generate another pair, these two holes will generate another pair. So this way it will keep on multiplying. So this process does not stop. So now when this will happen? When the depletion width is larger than the mean free path of collisions, right? So there's a lot of collisions are taking place. So we were discussing that for avalanche breakdown, very high field causes these carriers to gain enough energy to knock down the electron hole pair, to create a electron hole pair, and these electron hole pair again generate another set of carriers. So this way they keep on multiplying. Now if you recall, what is the expression for maximum field? Maximum field is basically 2q bbi minus ba by epsilon times n inverse plus n d inverse, right? So this field will increase with a applied bias. So if your bias, reverse bias, is more than certain value. Now every semiconductor has certain breakdown field. So for example, silicon, it has some order of megavolt per centimeter. You have germanium, you have gallium arsenide, and this breakdown field actually depends on the band gap. If the band gap is large, breakdown field will be more. If band gap is small, breakdown field will be small, because it's easier to generate electron hole pair. So when at the certain applied bias, if field reaches the critical field, right, where this electron hole pairs are generated, is called E critical. So at critical field, this avalanche breakdown takes place. So you can write here, let's say E critical square will be, you square this thing, and this is VBR is a breakdown field. It's usually quite large, so you can ignore this VBI. And then if you see here, the design parameter of the diode, because Q, epsilon, these are constant for a given material. With the doping, if you see, the breakdown voltage is proportional to, because EC is constant. Now this EC is not the conduction band energy, right? This is the electric field, the critical electric field. So this comes out to Na plus Nd by Na Nd. Now if both the dopings are same, if Na and Nd are equal, it is basically 2 by Na or Nd, right? If it is one-sided, let's say Na is large, so this will be basically numerator will be Na only, denominator will be Na Nd, so this will become 1 by Nd, right? So this is inversely proportional to the less doped concentration, less doped regions doping. So that means if you increase this doping of the lower doped side, the breakdown voltage will decrease. The breakdown will occur at smaller voltage. Okay, so this is the written here that we discussed. So magnetic carrier get accelerated in the depletion region by the electric field. They lose energy through collision and generate electron hole pair. So they knock out more carriers, and these carriers again do the same thing, right? So there's a huge multiplication in number of carriers. This is called avalanche breakdown. Now experimentally, people have reported that the breakdown voltage, how does it change with the doping? So of course, this is the doping of the lower doped side. That means other side is highly doped. This is a lower doped. So if you increase the doping of lower doped side, the breakdown voltage decreases, right? From expression we found it's inversely proportional to the doping. But experimentally there is a power here 0.75. You can see these curves, and you can see one more thing here. The breakdown voltage is higher for gallium arsenide because band gap is higher, around 1.4. Again, it's lower for silicon, band gap is around 1.1. It's even lower for germanium, band gap around 0.6, 0.7. And then if you go to here, this is basically there is a change in the slope here also, right? So this is the experimental data which shows basically how the breakdown voltage change with the doping. Now let's say there is another material whose band gap is 2 electron volt. So where the curve will appear? At bottom, means at the top or at the bottom? For band gap 2 electron volt. Okay. Now another breakdown mechanism is called Zener breakdown. Now in Zener breakdown, what happens? This depletion region acts like a barrier, and this particle can tunnel through this barrier. Now there are two things that are required for Zener breakdown. Number one, this barrier should be narrow, right? So D should be very small, and you can calculate the turning probability for a given width, right? So you can estimate, let's say for silicon, what should be the value of D. And another one, when electron tunnel from left to right, there should be state here. Let's say this region falls under band gap. Then even if this barrier is narrow, this particle cannot tunnel through it, because the particle that is tunneling, it should have same energy on both sides. Otherwise you have to increase the energy, then it can tunnel, right? So there should be state here. That means the potential should be lowered in such a way that this balance band and the conduction band here align. So if you, let's say you think in terms of varying the voltage, right? So initially they are somewhere here, then you go it down, right? So they will appear only after certain voltage. Now usually see Zener breakdown occurs at lower voltage. You see the band gap. What is the band gap of silicon? Around 1.1 electron volt, right? So it should be order of few volt only, where these carriers can tunnel through it. So two things are required. Narrow barrier means high doping, right? High doping. And then state should be there. It means it should be few volts, right? So that carrier can tunnel through. And you can see here VBI plus VA minus V applied. This is again in reverse bias. Now tunneling will occur only reverse bias, right? In forward bias you don't have that case anyway. So this should be now minus V applied is V breakdown, right? So VBA plus VA should be more than the band gap energy. But the IV curve will look same, because now carriers can tunnel through it, so large current will flow. So in case of reverse bias, the current curve will look similar, whether it is the avalanche breakdown or the Zener breakdown. Now let us discuss the third case, generation recombination current under reverse bias. So far we assume that there is no generation recombination here. Now let us discuss the reverse bias, then we will discuss the forward bias. So in case of reverse bias, carriers are less in concentration here. So that means NP product is less than Ni square. So Np minus Ni square is negative. So that means there will be net generation. So in reverse bias, you will have generation current. So carriers will be generated in the depletion region and they will flow out according to the electric field in the depletion region. So you can write RG current is Q times A times the carrier generation times the total carrier generation in the depletion region, right? So you can write carrier generation rate multiplied by the length of the region. So generation net recombination rate is Np minus Ni square divided by tau P times N plus N1 plus tau N times P plus P1, right? Now here Np is quite small, so this you can approximate as minus Ni square divided by tau P times N1 plus tau N times P1. Now for certain case where your trap level is just in the middle, N1 P1 are almost equal to Ni, right? So this is basically minus Ni by tau N plus tau P, right? So this will be your generation rate here, and then you multiply by dx, you will get the generation current, right? So length is basically W, so this becomes W, the width W of the depletion region. Now you notice here this current is proportional to the width of depletion region, and width of depletion region is proportional to the square root of voltage, right? So that means your generation current will be proportional to the square root of voltage, right? You can see here detailed derivation. So dN by dt is basically Np minus Ni square by the denominator term, and when you integrate over dx, now this is more or less constant, because current is the carrier concentration is very small, right? It's not varying. So you can just write W here, integral dx become W, and W is this expression square root of V. So your generation current here is proportional to the square root of V. And And this 2 tau naught, basically assuming that tau n and tau p are, if they are equal, you can write here 2 tau n or 2 power tau p. Or you can just define another effective lifetime, tau naught, which is basically this denominator is tau naught. So tau naught becomes half of the denominator here divided by ni. So we have taken 1 ni here. So 1 ni is divided here, right? So you just ni here in the numerator. So reverse saturation voltage is proportional to the square root of reverse bias. And denominator this tau naught comes, which you can measure. So if you measure the reverse saturation current with voltage, how it is changing, it will be square root of this voltage, and other factors you can calculate. Ni is known, area of course you can customize, Q is fixed. So from the curve fitting you can obtain this lifetime. So this reverse saturation current can also be used to measure the lifetime, but it will not measure individual lifetime tau n and tau p. It will measure the effective lifetime tau naught. Now in case of forward bias, what will happen? In case of forward bias, there will be net generation because NP will be more than Ni square, and we know that for forward bias NP is Ni square exponential QV by KT, right? So let's see. In forward bias, there will be generation current. So sorry, there will be recombination current because a lot of carriers are getting injected. There's a lot of carrier concentration here. They will recombine, and when they recombine, they contribute to the current. So again, we can obtain the expression from current from the recombination rate. So it will be same expression, dN by dt multiplied by dx, right, over the depletion width. Now here the depletion width is narrower compared to the reverse bias. So it plays a role at certain small voltage, as you saw in the picture, from 0 to 0.35 volt. In that region this generation current plays a role. So if you again write NP minus Ni square by tau n tau p. Now here, NP is much larger than Ni, right? So you can numerator, it will become NP. In denominator again you can ignore N1 P1, you will have N and P only. So you can write expression like this. Now we will use one technique to estimate this current, right? Now what we do, we calculate the maximum value of this integrand, and maximum value of this integrand will be constant integrand maximum when n plus p is minimum, right? So this n plus p is minimum, and that will be minimum when np they are equal, right? So when np are equal, each of them will become Ni exponential QV by 2 KT, right? So each of them will become basically NP will become square root of this thing, right, in the depletion region. So they become Ni exponential QV by 2 KT. So we substitute it. So of course numerator you have Ni square QV by KT, and denominator you have QV by 2 KT. Now this is much larger than Ni. So you have in numerator you have a term with exponential QV by KT. In denominator you have a term exponential QV by 2 KT. So overall the ratio will be exponential QV by 2 KT. So this is what you will get. So that's why at lower voltages in forward bias, your current increases with a slope of Q by 2 KT instead of Q by KT. Now in case of high level injection, what will happen? In case of high level injection, the injected carrier concentration is comparable to the majority carrier concentration, right? So again here NP is Ni square exponential QV by KT, right? So here now this is much larger than NN or PP, the majority carrier concentration is comparable or larger, right? So that means both will be almost same, right? So that means your every this both the minority and majority carrier concentration will be Ni exponential QB by 2 kT, and then again you use the diffusion equation, right? You will get expression exponential with QB by 2 kT, because for high level injection the carrier concentration is exponential QB by 2 kT. So whole diffusion and electron diffusion, when you add them, you have this exponential QB by 2 kT common, and the total current is again proportional to the exponential QB by 2 kT. So again at high level injection, now high level injection of course occurs at higher voltage. So when you reach VBI or around that point, you will have high level injection. Now if you try to further increase the current, your voltage cannot go beyond VBI, right? So the voltage across the junction, it will not cross VBI, right? So that means rest of the voltage will drop across this series resistance, right? So now this equation exponential QV by KT, right, will become V minus the drop across the series resistance, right? So that's what you will have for even higher bias. Your series resistance will play a role. Of course, you can add both these resistance from the P region and N region and call it RS. And this V is replaced by V minus the drop across the series resistance, right? So the V at junction will be V minus I times RS. So this will again reduce the slope. So let's summarize. So in summary, your real diode IV curve can be broken into few regions. So this region is called breakdown region. This is reverse bias. In reverse bias, current is proportional to the square root of voltage, and this current is called generation current. This is called generation current. At a smaller forward bias, you have recombination current, right? Then of course you have this ideal region. Then beyond ideal region, when you are close to built-in potential, you have high level injection. This is high level injection, right? And then beyond high level injection, you have effect of series resistance. Now series resistance play a role at high current, right? If current is smaller, series resistance, the drop will be very small. Now this is basically the assumption that because the doping is high, so in the quasi neutral region there is no drop, right? But with high current, when the current is very large, this is not valid, right? So we will have to take into account the drop in the quasi neutral region. Okay. Now let us consider a PN junction with narrow base. Now if the base of the PN junction is narrow, right? So it is cut down here. Cut down here, what will happen? Now at this junction, the concentration has to go to 0 here, right? So your slope will be, instead of 1 by L, slope will become 1 by W. Instead of 1 by L, slope will become 1 by W, right? So in the expression for the current, you can replace L by W here. So this is W for N, W for P, and that will give you the overall current. For the narrow base PN junction diode. Now both of them can be narrow or one side can be narrow. So depending on which side is narrow, you can use this expression. Now there is a quiz for you. Please try this quiz. Now this is the model of depletion layer, right? What we assumed in the depletion region, there is a positive charge here, there is a negative charge here. Now these are fixed charges, right? So this is basically ND plus, right? Q and D plus. This is Q and A minus. And of course, this is an approximation, right? So a more realistic picture will be if we include the carrier concentration here also, right? So instead of this QNA, we write it QNA minus, because this minus charge, you remove the whole concentration, right? And here you write QND minus electron concentration here. So what will happen? Now this charge will not be fixed. This charge will, may show some variation like this, right? So in that case, please calculate what will be VBI. Now in time giving you the derivative of d by dx, or you can write d2 psi by dx square, right? Will be rho, right? Q times Na minus P for whole side, and Nd minus N for N side, right? And P, of course, you can assume that now for P side, P is actually Na, right? That's what we assume, right? But let's assume as you are moving away from the neutral region, this is changing, right? This is changing with the potential. If you see the potential here, let's say this is your Fermi level. Now in let's say in equilibrium, Fermi level is constant, right? So this is let's say N side, this is P side. So N side balance band conduction will be here, right? So, and this is just the potential, right? Or minus Q psi. Now Fermi level is here. So the potential difference, right? So here the concentration is Na basically, right? Now as you move away, this is changing. So this potential is changing. So now gap between the Fermi level and the conduction band is changed by this potential Q psi, right? So the concentration will whole concentration will decrease by exponential minus Q psi, right? So you can write your P is basically Na times exponential minus psi, right? And this coefficient will becomes Q by KT, right? So if you substitute it, you can try this one, right? And please try to obtain the expression for built-in potential in this case. Okay. And with this, I'm closing the lecture. So please feel free to ask any question.